Today we have Gaku Nishiyama, and Gaku is a postdoc and he works at DLR at the moment in Germany. He got his PhD in Earth and Planetary Sciences from the University of Tokyo only quite recently, last March. Since the start of his PhD, Gaku has been working on multiple planetary exploration missions, including Hayabusa 2 and currently Bepi Colombo and JUICE. And on all those missions, he has been a member of the laser altimeter teams. His expertise is mainly in planetary geology and geodesy, but as we will hear, recently he also started working on infrared measurements of the solar system bodies using meteorological satellites. And so today he will present his recent work on the Moon and Venus, utilizing data from the Japanese meteorological satellite Himawari 8 and 9. So, without further ado, Gaku, take it away.
Thank you so much for your introduction. So, nice to meet you. I'm Gaku Nishiyama, a postdoc working at DLR, and today my talk topic is about meteorological satellites. The main topic or main, take-home message actually is we can use meteorological satellites for planetary science. And today, mainly, I will talk about our recent studies for the Moon and Venus by using meteorological satellite data. But I think it maybe sounds a bit weird, so let me start from a basic concept of this study. So here, well, it's not working. Yeah, so here, this is the image of the Earth taken by Japanese meteorological satellite Himawari 8 and 9. And of course, this is meteorological satellites, which means we observe the weather on the Earth. And we take this kind of full disk Earth image every 10 minutes or so. But in this image, sometimes you can find celestial bodies. Like, for example, maybe some of the audience have noticed that there is the moon. So this is actually the photo taken by Himawari. So you can see the moon quite nicely, and also sometimes you can find other solar system bodies like Mercury, Mars, Jupiter, and also Venus at a wide range of phase angles, from the crescent Venus to almost full Venus like this. So today's topic is how we can utilize this meteorological satellite data for planetary science. So recently in our studies, we proved that meteorological satellite can be a space telescope. And today I would like to show how useful they are. So let's start from some basics of Himawari 8 and 9 meteorological satellites. So as I said, Himawari 8 and 9 is Japanese geostationary weather satellites that observe the Earth, and it's operated by JAXA and Japan Meteorological Agency. And maybe I would like to mention that the reason why this is called Himawari. So Himawari is in Japanese means sunflower. Of course, sunflower is looking at the sun. That's why these meteorological satellites are named Himawari series. And this Himawari series takes the image every 10 minutes. And we actually have two Himawari satellites nowadays. The first one is Himawari 8, which was operated from 2015 to 2022, and now it's in standby mode as a backup until 2029. And now we have Himawari 9 data, which is a successor of Himawari 8, and which is operated from 2022, and then it's still working. And the operation is planned until 2029. So these satellites take the image every 10 minutes to see the weathers around the Earth, on the Earth, and also especially around Japan, because maybe, as you know, Japan is always suffering from natural disaster like clouds, typhoons. And this high frequency measurements enable us, for example, track, I think you can see, yeah. Now I think you see some cloud motion here. This is movie of actual image. And so these Himawari series are supposed to measure this kind of weather conditions every day. And also the other characteristics is that Himawari 8 is equipped with 16 bands from visible to mid-infrared wavelengths. So there is plenty of bands that would be useful for planetary science as well. I will come back to this point later. And also another point is that all data is open to the public, so anybody can use this data. So these Himari satellites could be useful for planetary science, and as I said, they can observe celestial bodies. But why can they observe celestial bodies? The reason is Himari 8 and 9 scans the Earth from west to east, including space. So I will show a scanning sequence in the movie on the left-hand side. Here, I think you can see the Earth is being scanned by Himari. And basically, Himari 8 and 9 scan the Earth from west to east and repeat it from north to south. And maybe you can see that here, the scanning starts from the space. So which means space adjacent to the Earth is also imaged in this Himari 8 and 9 observations. And if you look at this space, sometimes you can find stars or planets. So for example, here is an example of Betelgeuse, star Betelgeuse. And here you can see the Earth, and you can see small, tiny, and if it's just 2 or 3 pixel size, it's really bright. And this is Betelgeuse. And if you get the brightness of these pixels, then you can track, for example, Betelgeuse grid dimming like this. So, Betelgeuse is changing its brightness due to many processes. So Himari 8 and 9 repeats this kind of observation cycle at 10 minutes interval. Then we have plenty of data that contain stars, planets at various timings and also at various phase angles, because these meteorological satellites can conduct observation whenever the sun is behind the Earth. So even if the angular distance from between the stars and the sun is just, for example, 5 degrees, you can do observation because the sun could be behind the Earth. So this is one of the main characteristics of Himari 8 and 9. And also, as I said, we have 16 bands at visible to infrared wavelengths. Here I'm showing band positions of Himari 8 and 9 detectors. And so here x-axis the wavelengths, and then this number shows the position of each band. And we have 3 bands for visible and 3 for near infrared, and also 7 for mid-infrared wavelengths. 10 for mid-infrared wavelengths. And the resolution is a bit different, but the highest resolution is like 0.5 kilometer on the Earth, which corresponds to 14 microrad in angular resolution. And in the infrared, the resolution is a bit worse, but it's still like 2 kilometer on the Earth and 56 microrad in angular resolution. And the point is that we have plenty of bands, and also sometimes, so the gray shade shows the absorption of the terrestrial atmosphere, but sometimes we have bands outside atmospheric window. So at these bands, the observation from the Earth is quite difficult because of the atmosphere, but Himari 8 and 9 can conduct observation because it's in space. And today I would like to mainly talk about mid-infrared because it's really interesting wavelength range in planetary science. And if you compare this Himari 8 and 9 coverage in mid-infrared, there are many overlaps with other space exploration missions. Here I'm showing the coverage of Himari 8 and 9 with red shades, so x-axis wavelengths, red shade is the position of Himari 8 coverage. And I plotted several infrared camera and spectrometers and their coverage. For example, in the case of the moon, we have lunar reconnaissance orbiter, and then that has diviner radiometer, and which is composed of several channels, and 3 of them are looking at 8 micron, and also the next one is like actually looking at wavelengths above 13 micron. So Himari 8 can see other bands that has not been covered by LRO. And for example, in the case of Venus, we have long infrared camera on board Akatsuki mission, Plan-to-See mission by Japan. And this camera is a single band camera that covers from 8 micron to 12 micron. But in the case of Himari, we can resolve this wavelength range with 4 bands. So what we can say here is that sometimes Himalaya 8 and 9 covers the planets, the wavelengths with higher spectral resolution compared to existing data. And also there are many overlaps. For example, in the case of Akatsuki, we have overlaps with 4 bands, and also in the case of Diviner, we have almost complete overlap at this band. So comparison with Himalaya data could be done in terms of instrument calibration, and that could be helpful for any planetary science missions. So today, based on these facts, I'd like to introduce our recent studies utilizing Himalaya 8 and 9 data for planetary science. And recently, it's maybe not recent, but 3 years ago, we have published a paper about the moon seen by meteorological satellites in Earth, planets, and space. And actually, in this paper, we succeeded in extracting some physical properties of the moon lunar surface by using infrared data. And also recently, we have published a paper about Venus, and we actually succeeded in detecting atmospheric variation, temperature variation over a decade. And also we observed variability of planetary scale wave structure in vertical profile. So, and also now we have some collaboration with other planetary science all over the world, and so the topics are covering like calculation of infrared instruments on board planetary missions, or we also have collaboration on Mercury by using this data. And also some colleagues are now using this data to test the method for exoplanet characterization. And also we have other data like planet, Jupiter, or Mars. So today I will introduce mainly about these 2 topics about the moon and Venus, but after that I will talk about other topics as well. So let's start the lunar topic first. So as I said, we can see some physical property of the moon by using mid-infrared. And this is actual image taken by Himalaya 8 in the mid-infrared wavelengths. And unfortunately, the resolution is a bit worse compared to visible wavelengths, but still you can see spatial, variation. For example, you can see crater here, or yeah, this is actually corresponding to Mars. And of course, this is mid-infrared wavelengths. So you can convert this brightness to temperature like this. And you can get temperature variation on the moon by using meteorological satellites. And if you look at this temperature information at multiband or at various wavelengths, you can get information on, for example, surface roughness and also rock abundance. I will talk about it today. So the reason why we can see surface properties in infrared radiance is that these properties are affecting radiation. Imagine that if you have surface roughness, for example, the surface is not flat, you have small curvatures like this. And if you have, or in the morning or evening side, then the altitude of the sun is quite low. In that case, you have, for example, sunlit side, which is really hot, and shadow side, which remains quite cold. So there would be temperature variability in the small scale if you have roughness in the morning or evening. And this is also the case if you have rocks. And you can see such temperature variation in a small scale in night because of the difference in thermal inertia. The thermal inertia is a parameter that defines how fast materials are cooled down. And in the case of rock has higher thermal inertia, which means rock stays warmer compared to the sand in the night, which makes the temperature mixture in a small scale. So if you have such kind of temperature variety within a small scale, for example, within a pixel of the infrared image, then what you can see is the brightness temperature difference among wavelengths. So here I'm showing a schematic, it's kind of example, but if you have, for example, 300 Kelvin surface and 100 Kelvin surface mixed within a pixel, then you could get radiance as a function of wavelengths like this. So this line cannot be fitted with a single Planck function. And for example, if you look at the radiance at 8 micron, then this radiance corresponds to a black body of temperature with temperature of 270 Kelvin. But if you look at, for example, 40 micron, you can see the temperature of 250 Kelvin. So there would be a difference in brightness temperature among the bands if you have such temperature mixture. So if you have a multi-band measurement in the infrared wavelengths, you can get brightness temperature difference among wavelengths. And then after comparison with models, including roughness or rock abundances, then you can estimate these, surface roughness or rock abundance from infrared measurements. This is really actually classical way to assess surface properties by using infrared measurements. But it's really important because, for example, rock abundance is crucial to select landing sites in the future. And so we aiming to this, to derive surface properties, we archived all the lunar images taken by Himari 8 and 9. And I'd like to show some examples, but it's actually a bit tough work because you have to select the images mainly by hand. But here I'm showing the lunar images taken by Himari 8 and 9. And because this is meteorological satellites and the moon is sometimes close to the Earth, so the lunar image is sometimes affected by the Earth's atmosphere, or also as I said, the Himari 8 do the scanning observation from west to east and repeat it from north to south, which means sometimes the moon is cut by scanning swath, and you cannot get full moon like this. And also, of course, the scanning area is still close to the Earth, so sometimes the part of the moon is outside the scanning area, so you cannot get the lunar image like this. But you can find some lunar images that is not affected by this, by the Earth or scanning area. But still, there is some problem because the moon is too hot compared to the Earth. And the pixels are saturated, but you can still see temperature in the morning and evening. And taking these images, you can derive temperature curve of the moon. So here I'm showing lunar temperature variation derived from Himari 8 and 9 data at this wavelengths. And so x-axis is local time, so 0 is midnight on the Earth, and 6 is morning, and 18 is evening or sunset time on the Earth, on the moon. And you can clearly see a temperature variation among local time. And first you can see a temperature rise in the morning, and then it reaches to saturation level. But you can see a decrease of temperature, and you see still a decrease of temperature in the night because the sand or rocks slowly cooled down due to radiation. So except for the moon, you can track lunar temperature like this at various bands. What we did by using this data is first comparison of brightness temperature among different bands. For example, here I'm showing brightness temperature difference between band 11 and 15. And so the y-axis is temperature difference, and you can see that the temperature difference increases with decreasing solar altitude. So this is consistent with the roughness effect that I explained in the previous slides. And what we did next is we made a simulation of lunar thermal radiation, including roughness effect, and then we compared that with observations and simulations, and we found that of course you can tune the roughness parameter, which is defined as mean slope, and we found that the mean slope of 16 to 20 degrees can make the simulation that matches the observation. Interestingly, if you look at the observation at upper landing sites, the mean slope angle is like 15 to 28 degrees, which is quite consistent with our observation. So here you can say that Himari 8 and 9 can be used to derive surface roughness on the Earth, on the moon. And also, as I said, night side data is useful to see rock abundances because rocks are warmer than the sand. And Actually, if you look at the lunar image in the night side, it's really interesting. Here I'm showing the radiance of the moon in the night side in a log scale. And you can see some bright spots here, here, and also here are some bright spots here. And actually, these are corresponding to young craters. Because once you have a crater formation, the crater formation exposes rocks, below the regolith layer, then you can have many intact rocks on the surface. And these rocks will be collapsed by micrometeorite impact after, I think, 1 giga years or later. But if you have young craters, such rocks are still existing. So you can see such rock abundance if you look at multiband, infrared wavelengths. And for example, if you look at Tycho crater, here I'm showing brightness temperature as a function of wavelengths. And so black points are data. And you can see a nice, dependence of brightness temperature on wavelengths. That implies there is rocks, of course. And what we did is making rock temperature model and sun temperature model based on Apollo, samples or in situ measurements. Then you can make a kind of mixed model. I mean, temperature of mixed rock sun mixtures. And then you can also change the rock abundance values as a parameter, and then you can feed it to the data. So here I'm showing mixture model result with several colors. And as you can see here, around 10%, the model agrees with the observation well. Actually, by using over the data, we found that the rock abundance at Tyche crater is 6 to 10%. And also we can do this kind of estimation for the crater. And we derived that the rock abundance is like less than 0.5%. These values are actually consistent with previous estimates. So I would say Himari 8 and 9 can be used to estimate rock abundance as well. So the message from this work is that Himari 8 and 9 may be utilized for studying lunar thermal environment. That would be quite useful for future studies. Then, so this is all about our lunar work by using Himari 8 and 9 data. And then after that, we moved on to Venus because Venus is more interesting body in terms of long-term, observation, because Venus has, thick atmosphere that could variable in time. So we archived all the Venus data taken by Himari 8 and 9, and here I'm showing some example of the images. I think I have shown these images in the second slides, but if you look at the infrared bands at the same time, the Venus looks like this. So because of the limited resolution, Venus is almost like just with a size of few pixels. So you cannot get any spatial variation in temperature on Venus, but you can derive disk integrated radiance. And that can be derived at various phase angles, as I said. And Himari 8 and 9 can conduct observation whenever the sun is behind the Earth or whenever the sun is outside the scanning crater. So you can get the data at the variety of phase angles. And actually, I'm here showing all the observations, histograms, as a function of sub-Himari local time. So x-axis is the local time and y-axis is the number of observations, and the colors shows observation year. But you can see that almost all the local times have been covered by Himari 8 and 9 observations. And if you look at all the data, then you can see temporal variation. Here, I'm showing all the data points as a function of observation year and also brightness temperature in the y-axis, and the colors shows the different bands. And well, and when you look at this plot, probably you can find there is first of all, we have 400 observations, and then you can find temporal variation like this. And we have archived all the Venus measurements from data taken by February this year. And Himari 8 and 9 succeeded in observing temperature variation on year scale like this. And also, if you look at a certain time frame, for example, if you look at here, then the variation is like this. Actually, you can also see a variation on days scale. So Himalaya 9 data can help to see, variations on various time scales. And also, I have to mention that this data can complement the missing periods of previous Venus observations. For example, we had Akatsuki mission from Japan, and Akatsuki arrived at Venus around the end of 2015, but it's officially ended last week because of communication trouble between spacecraft and the Earth. But Himalaya 9 has started its observation before the arrival of Akatsuki and still continuing, which means we have more data than Akatsuki in terms of time range. So this data can be quite useful to track this long-term variation of temperatures. But what can we see in this temperature data? I have to describe this point by looking at spectrum. So here I'm showing example of spectral radiance of Venus, and you can see many features. There is a depression here, and it's not flat. The reason why is there is, clouds and atmospheres in the case of Venus. First, we have clouds composed of H2SO4, which causes variation because the scattering coefficient is different among wavelengths. And also we have, in the case of Venus, we have SO2 or CO2 as a main absorption source. And as a result, the transparency of the atmosphere, optical thickness of atmosphere is different among wavelengths. So at some wavelengths, you can see, temperature at high altitude, but at other wavelengths, you can see temperature at lower altitude. So what you see in this spectrum is the radiation from different altitudes. And once you calculate weighting functions, that describes where you see with this band. And here I'm showing weighting function, so as a function of altitude in y-axis. And for example, if you look at band 16, the weighting function is like this purple line. And you can see that this band is sensitive to altitude around 70 kilometer mainly. And if you look at band 8, black blue line here, then you see the altitude of 65 or even lower is sensed, is detected in this band. So multi-band measurements of Himalaya 9 can provide information at different altitudes in this altitude range. And you can see the, many vertical structure by using multi-band measurement in the case of Himalaya 9. But what we see in this long-term multi-band infrared measurements, and we have to come back to this point by considering the thick atmosphere of Venus. And actually, this kind of observation is really important to understand superrotation of Venus. As you know, Venus has superrotation, which rotates its atmosphere rotates much faster than the planetary rotation. But this superrotation speed is also changing in time. Here I'm showing mean zonal wind speed observed by Venus Express and Akatsuki orbiter. And so x-axis observation year and y-axis is the speed of wind, superrotation speed. And you can clearly see that in the era of Venus Express, you see an increasing trend like this. But in the era of Akatsuki mission, you have rather decreasing trend. And the variation is actually really large. It reaches 30% actually. And this the cause of this variation is still under debate. Maybe albedo variation of Venus causes such kind of change, but another point that might be important in this variation is wave structure variation, because superrotation is driven by many types of waves. So here I'm showing some schematic images of the interaction between superrotation and various wave structures. Basically, as I said, Venus has superrotation, but that is, Akatsuki has revealed that the superrotation is maintained by thermal tide, which is gravity wave caused by sunlight absorption. And actually, if you look at temperature field of Venus, here I'm showing Venus temperature field as a function of local time and latitude. And you can see a pattern of temperature, which is fixed in terms of sunlight position. And this is actually gravity wave that can be seen in temperature field. And this gravity wave, thermal tide, is transporting angular momentum to cloud layer that maintains superrotation of Venus. And actually, thermal tide is composed of mainly two components. One is diurnal tide and semi-diurnal tide, and the balance or these tides are also important to understand the interaction between thermal tide and superrotation. And also, in the case of Venus, we have other waves, like, for example, Rossby waves, which we can also see on the Earth. And this kind of waves is also interacting with superrotation. So we have to understand these waves first to understand superrotation. And there is still a question that is, how stable are these wave structures over years? Of course, we need long-term observation on this point, but we still miss such observation, unfortunately. But Himari 8 and 9 can help understand the stability of these wave structures. That is what we did. And and then first we took a look at thermal tide by using Himari 8 and 9 data. And here I'm showing brightness temperature as a function of local time again. And you can see maybe some patterns, but it's not so clear. But interestingly, so the colors shows the observation year. And if you limit the plot to the observation of first 2 years, so the temperature pattern looks like this. Actually, as you can see here, the temperature pattern is like temperature has a maximum value around the morning, which corresponds to weak diurnal tides. But if you look at the last 2 years, then the plot is like this. So in the morning, the temperature is the minimum, and which corresponds to strong diurnal components of thermal tide. So there is a variation, temporal variation of thermal tide structure, which is detected by Himari 8 and 9 data. And this is really interesting observation, and that would be quite helpful to understand in the future, to understand the Venus atmosphere dynamics in the future. But Himari 8 and 9 can provide observation basis on this point. And also, we next look at Rossby waves, and we also found some interesting points. Like, for example, here I'm showing temporal variation of temperature at band 8, 13, and 16. And you can see that, for example, if you look at band 8, the temperature has maximum right here, but you have no peaks at band 16. This kind of variation is happening at date scale, but there is variation in terms dependent on altitude. And we analyzed this point by using periodogram analysis. Then here I'm showing the results. X-axis the period of the waves, and color shows amplitude, and y-axis shows the band numbers, which is sorted based on altitude. So, and you can see that, for example, here, you can see 5-day period Rossby waves. But this amplitude is decreasing with altitude, and if you look at altitude higher than 68 kilometer, you have no Rossby wave structure. So amplitude decrease with increasing altitude was detected in this Himari 8 and 9 data, and actually this is the first detection of this wave structure in the world, I think. And also you can do this kind of analysis for other time frame. For example, here I'm showing the amplitude of 5-day Rossby waves as a function of band, and here is amplitude, and also the color shows the different time frame. And you can see that there is a variation actually in the case of Rossby wave structures. And also, if you compare global circulation model by Takagi et al., you can estimate, we can, predict the amplitude of 5-day Rossby waves, like this black point, that black dashed lines. But sometimes it agrees, but sometimes it's not. And this kind of data by Himalaya 9 can provide observational constraints for this kind of models. And also in the future, maybe by tuning some parameters of the models, you can consider what causes this kind of variation in terms of atmosphere physics. So also we have observed that brightness temperature structure, the temperature structure in vertical profile is also changing. For example, in 2024, the temperature at altitude higher than 70 kilometer is warmer. But if you look at altitude lower than 70 kilometer, it's colder in 2024. So there is a variation in temperature profile, vertical profile temperatures. So this kind of observation will be helpful when you compare with the models to understand the climate of Venus. So I would say Himalaya 9 can provide such data. And also, I want to note that Venus will be monitored occasionally until the end of this satellite operation in 2029. So we can expect more data to consider this point in the future. So that's it about the Venus. But I'd like to mention other topics because this data is also used for other topics. And first point is calibration, as I said. So first of all, Himalaya 8 and 9 is well calibrated in comparison with other satellites because on the Earth we have many weather observing satellites which basically have similar band response functions of bands. And for example, in the case of Himalaya 8 and 9, we have area overlapping with the observation area of GOES satellite from the US at the same wavelength. So comparison with among the other meteorological satellites on the Earth, Himalaya 8 and 9 is calibrated with a typical error of less than 0.2 Kelvin. It's super nice. And so you can use this data as a kind of benchmark data for your calibration of instruments on board planetary missions. And we have done some comparison. For example, in the case of the moon, we compared the data with LRO diviner. Here I'm showing comparison. The LRO diviner has the value in this red shades, and the black points is Himalaya data. And you can see consistent data, which supports the calibration of LRO diviner. And also, you can do the same. We have done the same kind of comparison in the Venus data by using Akatsuki LIR data and the Bepicolombo Meltis data because Bepicolombo had a flyby at Venus. And during that time, Meltis observed the Venus atmosphere at the same wavelength range. And here I'm showing the comparison results. So the green point shows the radiance ratio of Himari over LIR, Akatsuki LIR, and also black star shows the radiance ratio of Meltis over LIR. And you can see that there is an offset from LIR, which means that there is underestimation of Venus temperature by Akatsuki LIR. We are now working on that point, so I have to say stay tuned for recalibration of LIR. But I want to say that here, so this kind of calibration can be done by using planetary observation by meteorological satellites. And also, we are now working on Mercury as well by using Himalaya 8 and 9 data. And this work is now led by Dr. Thomas Miller from Max Planck Institute for Extraterrestrial Physics. And here I'm showing Himalaya observations as a function of local time. And also y-axis shows the presence temperature. And you can see that Mercury is imaged at the wide range of phase angle as well. And you can see two lines here, and the color shows the Mercury sun distance. And actually, if you have Mercury farther from Sun, the temperature is, lower because, the sunlight coming to Mercury is less than that when you have Mercury close to the sun. So you can see such kind of variation based because of the this Mercury Sun distance like this. Now we are comparing thermal models of Mercury with this data, and then we are still working on this point, but we have made a model that matches similar data with an error of roughly 20% or so, but we still have onset at high phase angle. We are still working on that point, but in the future, maybe we can derive some parameter like roughness, surface roughness, or rock abundance of Mercury as well. So this kind of data could be useful to validate models before Bip-Colomb arrival, because after Bip-Colomb arrival, we would have data from Otis, but if you want to work on this point before the arrival, you can use this kind of data. And also, other colleagues from Japan are now using this data as an analog data for exoplanet detection. And nowadays, as you know, we can observe exoplanet by direct imaging. And here I'm showing an example of exoplanets, but the problem here is that the size of exoplanet in the image is just a few pixels, but we have to characterize the atmosphere or, rocky bodies from this exoplanet observations. But how can we do that? Now, Professor Shohei Aoki and Professor Takeshi Imamura from University of Tokyo is using this data to develop characterization method. For example, you can use Venus as an analog for exoplanets with thick atmosphere, and also, for example, you can use Mercury as an exoplanet with thin atmosphere. And for example, if you fit here I'm showing the radiance as a function of phase angles, but you can fit these points with, for example, Lambertian models, and then you can test if this reflection of this atmosphere can be characterized with these rows, and then they are now testing if this kind of characterization method can be useful for exoplanets or not. So this kind of data of solar system bodies taken by Himalaya 9 could be a data to test this kind of characterization method as well. And also we have other planet data like Mars and Jupiter. Here I'm showing Mars data as a function of Himalaya longitude and x-axis, and y-axis is radiance, and you can see some patterns actually. And this pattern is corresponding to albedo variation of the Martian surface, which has been already mapped by other instruments like TESS, but Himalaya 9 can still provide such data if you want to use. And also, what is also interesting is that in the case of Jupiter, we also see temporal variation. Here I'm showing radiance as a function of phase angle with a different observation year, but you can clearly see that there is a variation in time. So albedo has increased in time between 2016 to 2022. And so you can do this kind of temporal variation analysis in the case of the Jupiter by using Himalaya data. As I said, all the data of Mercury, Venus, Mars, and Jupiter have already been archived. And also we are happy to share the data with planetary science community broadly. So if you are interested in, please contact us. So here is concluding remarks. So the take-home message from my presentation is, let's use meteorological satellites data for planetary science. And as I said, we have done some lunar work and Venus work to see some physical properties of the moon. And also we detected temporal variation of atmospheric dynamics over a longer period than space exploration missions. As I said, we have published papers. So if you are interested in, please scan these QR codes. And also, as I said, we can use meteorological satellite data. So, and the final message from me is that if you are interested in this data, feel free to contact me, and then we can start collaboration. That's conclude my presentation, and I'm happy to take questions.
Thank you so much, Gaku, for this very interesting presentation indeed.
Thanks.
Yes, there are already a few questions, which is great. So I saw that the first question came up quite early in the talk already by Gurai.
Yep.
And Gurai asked, is there any higher exposure mode for Himawari as well? If it would be longer than 10 minutes, it may capture less bright details, as
That's
well
a,
as if it keeps photobombing, right? So,
yeah, that's a really nice question. And actually, I want to do that to see, less bright points. But of course, this is meteorological satellites, which means we have the primary target is the weather on the Earth, and of course we cannot take any risk to break the meteorological satellites. So nowadays, at present, it's not possible to do such a coordinated or optimized observation for planetary science. We have to use the data that was luckily taken in the images. But maybe in the future, for example, after retirement of meteorological satellites, maybe we can request it. Actually, I have started that kind of activity with the agency, but it's a kind of matter of money. So let's see.
it's always a matter of money, I
Yeah,
think.
unfortunately, yeah.
We should buy the satellite and at the end of the mission, should buy it and
Yeah,
then we can just use it. Yeah.
yeah. Could be possible. Yeah.
Okay. There's another question by Thomas.
Mhm.
Are the Venus or Mercury data also affected by saturation problems? I guess like I'm filling in like you had for the moon, right?
Yeah, that's a good point. First of all, in the case of Venus, the temperature is too low to be saturated, so there is no problem for Venus. But in the case of Mercury,
Mhm.
that's a good point actually. But the size of Venus, apparent size of Venus, is smaller than the pixel size, so the saturation is not caused as far as I checked. But uh, the problem is that I cannot check the original data from
You mean Mercury? The size of
Mercury. Yes.
Mercury is smaller. I think you said Venus. The size of Mercury is smaller than the
Oh,
pixel.
sorry.
Yeah.
That's my
Okay.
mistake. Yeah,
Okay.
it's
Right.
about Mercury. Yeah. Of
Mhm.
course, Mercury's temperature can be up to 700
Mm.
Kelvin or so. It's, you know, extreme case. But um, yeah, but in the case of Himawari data, the mercury is too small compared to pixel size, so there is no effect in saturation, in terms of saturation. Yep.
Okay. So you showed Mars, Jupiter.
Yep.
Is there no Saturn? I'm surprised. Saturn is quite big and bright, no?
Yeah, it's a good point. I have not checked Saturn data,
Hmm.
but so my answer might not so be so correct. But actually, this work is done in a collaboration with my friends, and he has checked if Saturn is captured or not. That he
Okay.
said Saturn is not detected. Unfortunately, it's too dark because Saturn is too far away from the sun, so the reflection of the sunlight is of course low, and also temperature is quite low. And
Yes.
yeah, for example, in the case of even the Jupiter, it's quite difficult to detect temperatures because the temperature is like 150
Hmm.
Kelvin. It's almost at the noise level of Himalayan 9. So at some band, you can see, you know, faint Jupiter in the image, in the infrared bands, but it's still a bit difficult sometimes.
Understood. Okay. Any other questions here from the audience? You can type or let's see, is there another question that came up? Oh, yes, another question. Stand by once. Kurai, stand by once. I'm not sure what you mean exactly in with stand by ones.
Uh, can I
Yeah,
take a
Kurai. So, Kurai, would you like to talk or type a question in the
this one?
chat?
Standby ones.
Mm.
You mean the backup satellites? You mean so? For example, now
Oh, okay, the
Himalaya
satellites.
is
Okay,
in standard.
sorry.
That's a good point. That's a good point. But of course, if you have some trouble with Himalaya 9, Himalaya 8 will be used. So we have to keep Himalaya 8 in a safe mode. So we cannot use Himalaya 8 for
Ah,
astronomical observation. But of course, after retirement, it could be possible.
yes,
Let's
yes,
see.
yes, yes,
Yeah,
yes.
yeah,
Yeah.
good question.
Thomas has another question. He asked, would it be possible for a very bright near Earth or bright very near Earth object to be visible, very near Earth asteroid to be visible?
Yeah, that's a
It's a good
really
one. That's a good
good
one.
question. Yeah,
They
yeah.
will move very fast, though, probably. I don't know, because if
Exactly.
you're
So we have,
scanning,
yeah, so we have to be lucky, first of all.
yeah.
And as I said, the resolution of the image is like 2 kilometers on the Earth. So if you have kilometer size object
Hmm.
nearby the Earth, maybe it could be possible to detect them. But
Oh,
yeah, we have to be lucky. But okay, in terms of small bodies, there is a detection of fireball. So because if you have small bodies coming down to the Earth, of course we can see a fireball that is bright enough to be detected. There is actually a detection of fireball by meteorological satellite. So that kind of work can be done, but
yeah.
it might be not interesting for planetary scientists. Yeah,
Exactly.
it's more for the Earth. Yeah.
So there's Himawari 8, 9, but
Yep.
that means that there was a 6 and a 7 and
Yeah, yeah,
earlier.
exactly. This is
So
a
what
kind
happened
of
there?
yeah series. Yes, actually, I think the series started in 1990 or so, and we now have nine, satellites named Himawari, and then we would have global Himawari 10 in the future.
In the
So
future, yeah. But
probably, yeah,
those earlier ones have been decommissioned and they're not working anymore.
not working, I think.
But they don't have the same. They don't have data that's comparable to 8 and 9. Or was it a different camera
Yeah,
system or recording system? Or
good point.
that's
The camera system is a bit different
mm,
because of technology development. For example, compared to Himari 7, Himari 8 and 9 has, I think, the spatial resolution higher by factor of 2 or 3. And
right.
also, the number of bands has already been increased so much. So, yeah. But of course, you can use some bands to extract data, even with your with Himari 7 or 6 or 5. We have
So
not
that
done, but yeah, it
right.
could be
So there
possible.
might be
Yeah.
Venus data, for example, which could be a really interesting case because
Yeah,
it's
yeah,
so
yeah,
bright.
yeah.
Because of course, what is so interesting about this data, in my
Yes, yes,
opinion,
yes.
is that
Exactly,
the long
exactly.
time span that you have, which is very interesting.
Yes,
It's very
that could
difficult to
be,
get. Yeah.
yeah, our future work or we can
Yeah.
do in collaboration with anyone interested in
Hmm.
that. Yeah.
Yeah. Excellent. Okay. Any other questions from the audience? We are on top of the hour here, so if not, then I think we can finish our hour here today. Thank you so much, Gaku, again.
Thank you so much.
Thank you, Callum. Thank you, everyone who attended. And
Likewise,
we'll
thank
be
you, Martin.
back
Thank you, Gaku.
soon.